Did you know that in Switzerland there are scientists who are literally recreating the universe in a lab called CERN? Each day unlocking the mysteries of life down to the subatomic particle. Today, we're going to dispel the myths and learn what we know about space, time, gravity, and much more. To educate me on this topic is our guest. He's one of the most respected scientists alive. He's published over 1,500 papers, is a regular contributor on CNN, and has amassed millions of views on YouTube. Here's my conversation with Dr. Don Lincoln. You are a senior particle physicist at Fermilab, science communicator, author, PhD. In 1995, you co-discovered the top quark. In 2012, you co-discovered the Higgs Boson, otherwise known as the God particle at the time.
Mhm.
You're regularly involved in recreating the conditions of the beginning of the universe within 10 to the minus 13 seconds. So, my first question for you is, why'd you try to do something so easy in life, Don?
Well, it was just easier than, uh, breaking into Hollywood, I guess.
Well, that's a close second for you with your great YouTube channel. So I really do love that. Um, but let me ask you this. For the audience, I think it'd be propitious to hear from you to explain exactly what you do compared to, other science influencers out there like Michio Kaku, because what you do is actually, more consequential. I'd say you have more street cred, right? So describe the importance of what you do compared to, like, say, a theoretical physicist.
Well, okay, so you're comparing to other influencers. Most of the other influencers, I mean, the ones that people will know their names of, have, they earn their spurs doing research of some sort, but then have, redirected their lives, and that's why you see them because they're on TV and so forth more often. The the big difference is most of the influencers you will see, Kaku and Brian Greene and so forth, are theoretical physicists. So I'm not. I'm an experimental physicist, and I mean, I'm ongoing research. I've talked to grad students today. They're doing, the analysis they need to do, and so that's one big difference is that I maintain a strong connection to the research world, whereas many of the others in their success have found it difficult to split their time, and they made a choice.
Well, I'd say, what you do is kind of, you have maybe the most interesting job there is because you're literally seeing the beginning of the universe. So let's start there. Let's explain to people how this is even possible. So how are you able to recreate the beginning of the universe, with your work with CERN and this thing called the Large Hadron Collider? The names are so funky. Large Hadron. This is a funny name. I think the
It is.
last time I was at the Ale House Bar in Chicago. I think I got too drunk and I woke up with a Large Hadron Collider, but that's another story. But she came home with a new one, so it's okay. It's even. But tell me how is this possible? Let people know that it is the real thing.
All right. So people have heard about the Big Bang. They often have misconceptions, but broadly speaking, it says that the universe is expanding. And if it's expanding, that means it was once smaller. And if it was once smaller, as things get compressed, they get hotter. So from this, we can infer that a long time ago, about 14 billion years ago, the universe was much hotter and much denser. And that we're pretty confident that that's true. Now, we don't have a time machine. We can't go back and look at the universe as it was created, but it is possible to heat matter to the same temperatures that existed when the universe was very young. And so the way we do this, uh, personally, other people do it somewhat differently, is we take two protons. So we take basically hydrogen, we strip the electrons off. We accelerate protons to near the speed of light and we collide them head on. And these collisions are so violent that the temperatures that occur in the center of these collisions were last common a tiny fraction of a second after the universe began. And so we're not really going to the beginning of the universe, but it's recreating those conditions. So we can study what the universe was like a long time ago.
And tell us about the Large Hadron Collider. So describe the actual machine itself.
Okay, so the Large Hadron Collider is the world's largest particle accelerator. It is located in Geneva, well, just outside Geneva, Switzerland. It's big enough that it actually spans the Swiss-French border. Much of it is inside France. It is a ring of magnets, 27 kilometers, 16 and a half miles in circumference. It's actually just a tunnel. The tunnel is probably about, I don't know, 10 feet. So think of it as like a super skinny, very big bagel. Inside that tunnel are magnets, and these magnets cause protons to go around in a circle, and that's what magnets do. And so what we do is we have basically radio transmitters inside that make a large electric field. The electric field pushes the protons. The magnets make the protons go around in a circle. They come back and they get pushed again and go faster and faster and faster and faster. They go around about 11,000 times a second. And over the course of not very long, we accelerate it to near the speed of light. And that's what it is. It's just a big ring. It's a big racetrack for particles.
It sounds so simple, but obviously it's not.
I have
Uh,
people for that.
you allocate those the difficult things. Well, let's dispel, some of the Big Bang myths. I've heard you talk about this. I'm sure you're tired of hearing it. Or first off, we know Big Bang is true. We know this already. We know through Hubble's law we can see this, right?
Mhm.
Right? And one of the myths is for starters, it's not a Big Bang, was it?
Well, problem is words are often imprecise. So was it a big bang? Was it an explosion? Sort of. It was hotter and it's expanded. I mean, there's some commonalities with an honest to God explosion. But the problem is that most people think of the Big Bang as somehow the universe that we see, that Carl Sagan told us about, the billions and billions of stars and galaxies, were all compressed into a single spot with no size, which then exploded. This is what I call like the firecracker model of the Big Bang, and it's completely wrong. I mean, it's very common if you see animations, people are often show that it looks like there was a bang, and an explosion, and that's not really the case. We are not completely certain. Well, in fact, we are not at all certain of what the conditions were like either immediately before or immediately after the universe began. But the correct way to think of the Big Bang is not so much as an explosion, but as a stretching. So the universe that we see using the Hubble telescope or the James Webb Space Telescope, we can see very far away. We can see about 46 billion light years away, which is a staggering number. But, but, we know that the universe is bigger than that. The universe there's a place farther away that we can't see simply because there's not been enough time for light from that more distant location to get here. So this is a concern in the sense that it tells us that we're kind of a little bit fuzzy. But what we know is, or at least the data is telling us, that it appears in any one direction, whichever direction you point, the universe is about 500 times bigger, at least minimum, than what we can see. And that's in one direction. If you worry about volume, that's 125 million times bigger than the visible universe, which is a staggering thing. So we don't quite know exactly what happened, but just imagine that the universe that we can see is a sphere centered on Earth, and it's centered on Earth because the light from 14 billion years ago in all directions just getting us, and that is a spherical surface. But the universe is bigger than that. So that that shell, the visible universe, was in the past smaller and smaller and smaller. And at one point, it was very small. We do not believe it was a singularity, which a lot of people will tell you. But the idea of a singularity is using Einstein's theories and taking the math a little too seriously, because any physicist will tell you that when you get a singularity, it just means the math broke. But we do know that the universe was smaller, and it was probably, the visible universe was perhaps much smaller than an atom. So that's probably true. So to call it a singularity is close to correct, and that's why we can get away with it. At any rate, this universe was packed, it was small, something, we don't know what happened, it triggered the expansion of the universe. And so this ball, which is of what we can see, surrounded by more universe that we cannot yet see, decided to expand. And so that's the way to think of it. It's not an explosion. You cannot get outside the universe and look in. If you had a time machine, you could not go back and sit outside and watch it happen. You would be in the middle of it, and it would be very hot, and well, you'd need a cool drink after all that.
But so what do we know now about, so we know this thing should be renamed, but what do we know about the time from 0 to 10 minus 13 seconds? About
It's
this time,
mostly
what are they hypothesize about
well,
this?
well, hold on. Know and hypothesize are separate.
Okay.
We know very, very little prior to that. Why? Because we cannot recreate those conditions. Since we cannot recreate those conditions, what we're forced to do is to take the behavior of matter that we see somewhat later in time and take very good theories and test them to heck, all to death with that somewhat later time, and then project backwards. So what we think is we think that we don't understand what happened prior to the Big Bang. We don't understand what pulled the trigger. But the very, very early time, it seems like the universe expanded very quickly. We say faster than the speed of light, which is again one of those misleading things. But it did. It expanded extremely rapidly. Something of the ballpark, way, way smaller than a proton, to the size of, say, a soccer field in a tiny fraction of a second. And this is called inflation. Now, this is speculative. We don't know that inflation is true.
This is a different
However,
type. This is not Jerome Powell's inflation. This is
no,
a completely
no,
different.
no,
This is
no.
okay.
This is
This was
cosmic inflation,
uh,
and cosmic inflation was invented for a number of reasons, but it does do some explanations. It explains why when you look anywhere in the universe is basically the same, whether it's that direction or this direction, and that was a mystery until this inflation idea was proposed. The universe also seems to be on very large scales flat, meaning not distorted. And that's, again, very hard to understand if inflation isn't real. Now, that doesn't mean inflation is real, but we see these things, the flatness and the uniformity of the universe. And in 1980, inflation was proposed, and everybody went, oh, what a great idea. And we've been trying to look to see if that's true. And thus far, we have no definitive evidence, but it's a great explanation for the observation of the universe we see. So that occurred, this superluminal inflation happened for a tiny fraction of a second, at which point, at some time, it turned off. There was like a phase transition. So a phase transition is like water turning to ice, like where the laws change. I mean, we know what water is, we know what ice is. Ice is solid, water is liquid. They're the same, and yet they're not. And so the idea is that as the universe expanded, a phase transition occurred, the inflation turned off. And then we have what we sort of call the Big Bang, the universe expanding and slowing under the attraction of gravity. Before 10 to the minus 13 seconds, the atoms certainly didn't exist. Protons, neutrons didn't exist. Mass didn't exist. Electric charge didn't exist. Again, these are speculative ideas, but ones for which it's reasonable to think that they could be true. And at a time of about 10 to the minus 13 seconds, mass came into existence, charge came into existence. The particles of which we're currently familiar, real. Then the universe went on later. The smallest particles that we know of are called quarks. They're found inside protons and neutrons at about 10 to the minus 10th seconds. The universe was beginning to cool enough that they started to turn into protons and neutrons. That was finished by maybe a millionth of a second. Then time went on. I mean, it's still very short time, but it's a lot of things happening in the very first second. By about 3 minutes after the universe began, hydrogen and helium nuclei existed, but it was still too hot to make atoms. And the universe continued to expand and cool. By about 400,000 years after it began, the universe finally cooled enough that hydrogen atoms could exist. The universe was glowing orange hot at that time. It continued to expand slowly, and now you have like basically a gas that was cooling slowly, going from orange to dull red to eventually invisible, which happened, a couple million years after the universe began. Then it was dark until the gas clouds pulled everything together and stars started to form. And that is the childhood of the universe in a minute and a half.
Well, thanks for summing that up. I know that one of the strange things that happened that is still like a question is there's supposed to be equal amounts of matter and antimatter, right? And
Supposedly.
so walk us through why this is consequential and why that should have been during the when at the creation of the universe there should have been both.
Okay. So this is all Einstein's fault entirely. So
He's been the problem for way too long. Okay.
somebody's got to do something about him. Ah. All right. So Einstein came up with this equation, which has been validated, and it's the most famous equation perhaps in science, and maybe the most famous equation completely. E equals mc squared. And so you have E equals m, c squared is a constant. So E equals m, E is energy, m is mass. And what people often say is that energy can be made into matter and matter can be made into energy. So that's true. So you take this idea and you fold in some quantum mechanics and some really cool things. And what you find is that there was a prediction in 1928 that there should be, for all the matter, the kind of things that we're familiar, the stuff that makes up you and me, there should be a cousin stuff called antimatter. It's the antithesis of matter. They are antagonistic to one another. If you take matter and antimatter and combine them, they convert and form energy. So this was predicted in 1928. Antimatter was discovered just a few years later in 1931 by a guy by the name of Carl Anderson. And he first found the antimatter electron and then later found the antimatter proton. Well, he didn't, but antimatter proton, antimatter neutron. And we now know of antimatter all of all the particles. Now, the thing is, Einstein's equation equals mc squared that says, and we have tested this to incredible validity, when you convert energy into matter, you must make an equal amount of antimatter. And we absolutely do this. I mean, this is an experimental fact, and we've known about it for going on 100 years now, 100%. So energy converting into matter, you must make equal amount of antimatter. That's number one. Number two, we talked about this, the Big Bang. The universe was once much smaller, hotter, and full of energy. And as the universe expanded, that energy transformed into the matter that makes up the stars and galaxies. So we have energy must make matter and antimatter, but the universe once was full of energy, and so it should have made matter and antimatter in equal amounts because we've tested both of these to be true. And yet, we look at the stars, we look at the galaxies, and we see zero antimatter. And so that leads to the most troubling question of where did the antimatter go? And the answer is we don't know. We do believe that early in the universe, there was some tiny imbalance that we don't yet understand between matter and antimatter. So that for every basically 3 billion antimatter particles, there were 3,000,000,001 matter particles. And those 3 billions got together and annihilated and transformed to energy. And that one is the matter that makes up us. So laboratories around the world are studying this. My own laboratory, Fermilab, located outside of Chicago, is building an apparatus to look into this. But the short answer is we don't understand where that small asymmetry came from.
It certainly is a mystery, and we can only think that let's blame it on China. They must have stole all the antimatter.
Yeah.
No, you know what? You did mention this earlier that before the universe was created, that 10 to the minus 13, it traveled faster than light, but nothing can travel faster than light. This is true, right?
Nothing can travel faster than light through space. There is no restriction on how fast space can travel. So that's how you can get around this. So the if the universe, say at and I'm making these numbers up, but to give you the idea, say if uh, for every inch away the speed doubles. So an inch away, the universe is expanding at a certain speed. 2 inches away, it's double. 3 inches away, it's now times to the fourth and so forth. And eventually, if you go far enough away, what you find is you find that distant spot is moving away from you faster than the speed of light. And that is what we mean by saying that the universe expanded faster than light, because obviously near us, it would not have been moving very far fast, but very far away, that distant location was moving faster than, well, than light. And we even see that now when we look in our telescopes. So it's the the expansion of the universe is happening. It's happening here. It's right now, relatively slowly. But when you add up a little here and a little more from a bigger distance and a little more from a bigger distance and so on, eventually you get to a certain distance where that distant thing is moving away faster than light. And that is what we mean by that. Now, within space, moving from point A to point B, you can't go faster than light, but space can.
Okay, so there's an asterisk next to light speed. As long it's got to be space. Space can. Light can't, space can. That's what it is in
Right.
a
Well,
nutshell.
light travels in space. So by definition,
Right.
without space, light can't travel. So the asterisk is there, but I mean, basically, nothing can exist without space to exist in. So,
Now I'm
you just make
confused.
that assumption.
Okay, what about this, Don? Let me ask you this. Okay, so if light, nothing can travel faster than the speed of light, and why can't anything travel faster than the speed of light within space? The rules, the standard rule.
Beats me.
It's just it just
Well,
is
no, I
what it
mean
is.
that's a reasonable answer, and the answer is nobody knows.
Oh, really?
Um,
Okay.
well, I mean, there's I can explain it sort of, but why is it hard, right? I can tell you hows, I can tell you connections. Why somehow implies a purpose of some sort, some meaning, some reality. What I can tell you is that there is an ultimate speed through what we call space-time. So one of the things that Einstein came up with, well, he came up with, but one of his professors realized that space and time were interchangeable. They were connected. So what I experience as space, you might experience as time, and the third person might experience as partially space and partially time. And so if you um, if you accept that, and there's absolutely too much confirming evidence to not accept that. What we have discovered is that light travels through this combined thing, this space-time, at the speed of light. And so you can travel through space quickly, you can travel through time quickly, or you can travel partially through space and partially through time. But when you add up the speeds of in space and time, it's always the speed of light. And so that's why you can't go faster than the speed of light, because we always travel at just one speed. And it's just a matter of whether it's through time or space or both. And so that part I think is true. And that's part of the explanation of why we can't go faster than the speed of light. But now you ask, well, why is there a maximum speed? Why is there a speed that space-time can support? And that's where I go, I don't know. It's a property of space and time in the same way that space has a property of how much electricity it can support, how much magnetism it can support, how much gravity it can support. It's the property of space-time just has this limitation that,
Certain.
and the reason for reasons we simply don't understand.
It certainly is very interesting.
Mhm,
And so light travels one speed for all observers, right?
mhm.
And if let's say this though, let's say I was on your, how fast is your CERN Hadron Collider, your Large Hadron Collider? How
It's
fast can it
about
go?
it's 99.691% the speed of light.
So let's
So,
say I jumped on a ride on your Hadron Collider and I
mhm,
was riding, I had a gun
mhm.
and I waited till I reached 98%. percent speed of light, and then I fired that gun. Wouldn't that gun now be going, the bullet now be going the speed of the bullet plus
No,
the speed of the collider? No.
no.
Explain this.
And you can, I mean, I don't have a blackboard here to show it to you, but no, it turns out that when you use Einstein's equations correctly, um, you find that what you just described, which makes perfectly good sense, that if because in the slow world, if you're going 20 miles an hour and you throw a ball at 10 miles an hour, I'm going to see it at 30 miles an hour. And that's just true. But once you get close to the speed of light, it doesn't work that way. The velocities do not add in the familiar, intuitive way that we're used to. And so in the case that you described, instead of going, if you're going at 98% of the light per speed of light and you shoot a bullet with some high velocity, you might see it going 99% speed of light, but you'll never see it go faster than light.
All these rules. It
Yeah,
is.
yeah. And this sounds, we talk about we talk about this in the abstract with like guns and stuff. And so, of course, we can't make guns go the speed of light, but we can actually do a real test of what you described because subatomic particles, they can decay. And if they're sitting at rest, they will decay and you can measure their speed. Then you can take these same particles and put them in the accelerator and make them move very, very fast and let them decay. And we can measure the speed of the things that come out of the decay. And they never go faster than light, even though it's basically the same thing as your gun conjecture. But we can prove that they never, ever, ever go faster than light.
So that brings me to this then. So there is a paradox of quantum entanglement, right? Whereas
Mm-hmm.
it's a two. Can you explain how this works? Where two atoms are communicating with each other? Is that what it is?
Sort of. And it's very complicated, and there's a lot of hooey that's, you find on the web about this. So quantum entanglement has mysterious properties and non-mysterious properties, and unfortunately they get mixed together. The way you entangle two things is suppose you have some object which has a property that is zero, and it decays into two things. And in the decay, that property can't change. So it decays into one thing, and say that guy's got that has a property of one. Well, then the other guy has to have a property of -1 because it started with zero. And if you have two things, you've got one, the other one has to have -1, they add to zero, and everything's cool with that. So that's kind of what happens is we create particles and then we separate from one another. And they will always have the entanglement part is they will always have the opposite. Whatever one has, the other one will have the opposite of it. That's what entanglement means. And that in itself isn't so incredibly interesting because, if I told you you had a red sock and a blue sock, and that's the only socks you had, and I put a red sock in a box, then the other box is blue. You just do. But it is more complicated than that. And then you have to get much more deeper into quantum mechanics and probably more than you want to spend time talking about. But because the properties we're talking about are not color, they're not socks, they're not anything. They're things like the direction in which these particles act like they're spinning. And you start out with something with zero spin, and if one's spinning in one direction, the other has to spin in the opposite direction. That's just how it works. But because quantum mechanics, you can measure like the direction of which you're making the measurement, and it can be up and down or left and right. And you can like change your mind. In non-quantum mechanics, if in what I told you is true, if something was up, something is down, that's it, the end. But with quantum mechanics, you can later say, I don't want to measure up and down. I want to measure left and right. And in measuring one of them left, the other one pops to be right, even though you knew ahead of time that they were up and down. And so that's where quantum mechanics gets really wonky. But the entanglement part simply says that two objects created together can have properties such that they are basically mirror images of each other, no matter how far you separate them. And precisely what's mirroring Well, it depends on the measurement you make.
So it's not as spooky as everyone wants to believe it is.
It, yeah, well, like I said, it's quantum takes some doing, and if we talked about it a little bit more, it would get spooky again
Uh,
because of the fact that you might start out with it measuring in one direction, with something with in the classical world, something spinning up, it's never going to spin left or right because it's up. That's just how it is. But in quantum mechanics, when you measure it, it kind of decides, oh, you wanted to do left, right? Okay, I'll be left, right. And that's the spooky part. So that part's spooky. The entanglement itself is not so spooky, I don't think.
okay, so it's some sort of communication happening in between these things that
Yeah,
who
well,
knows what it is.
that's it seems like they're communicating with each other. But we've done experiments that says no, it's not. Whatever you think it is, it's weirder.
I'll take your word on it. Well, now I want to know this because this is something that you kind of blew my mind away with. I will ask you, where is all the matter?
Where is the matter?
Where is the matter? I hear this. I hear that you could take all the people in the entire world if you brought them down, took them down to their atoms, we all fill into a cup because we're mostly nothing. How is this possible?
Well, it's basically true. How is the solar system mostly empty? Now, the problem is, of course, when we talk about atoms, there are like different models. There is the little, you know, 1950s model of the atom with a little thing in the center and electrons swirling around it like planets, and that's not true. But there's some truth to it. Uh, if you want to think about quantum mechanics, there's a cloud, there's a nucleus at the center with a cloud of electrons. But when you ever find out, when you ever actually ask where the electron is, you find it at a certain spot. So basically, atoms are like little solar systems. And there's a lot wrong with me saying that because it's not that electrons are orbiting in the way that planets do. But that is sort of the answer to your question. It's just that um, atoms are mostly empty. And with this tiny nucleus at the center and this cloud of electrons around it, and whenever you actually look to see where the electron is, it's in one spot. And so it's like seeing asteroids around the sun, sort of.
But when you take these things apart, I heard you say that they lose weight at a certain space. Like a quark is the lightest, right?
It's the
Somehow when you weigh the
smallest.
quark,
It's
when you
this,
when you weigh the quark, somehow it loses its weight, its relative weight.
I think I know what you're getting at. So let me get at this. So the question is, where is your mass, you personally,
Ex
or any person out
exactly,
there?
exactly.
So you just make life easy. You have some gal weighs 100 pounds, all right? And so she weighs 100 pounds. Where is the mass? Well, first thing you do is you take all of the chemicals, you take them apart, which kind of ruins the whole thing. But suppose you did it. You took some apart and put them in a bucket, and so much oxygen, so much nitrogen, so much this, that, and the other thing. If they were 100 pounds, those atoms will weigh 100 pounds. No problem. So that tells us that the weight comes from the atoms. So now you say, well, I guess I start out with molecules. Weight is in the molecules. Now you take those molecules of whatever amino acid, something, something biology stuff, and you break those apart into the atoms. And you ask, what is the weight of those atoms? And that's also 100 pounds. So that just says our weight is in our atoms. Not so surprising. Now you say, well, we know that atoms are made of protons, neutrons, and electrons. And then so you say, well, where is the mass for those things? It turns out that the electron is very, very low mass. It's about 1/2000th the mass of the proton or the neutron. So the electron doesn't matter. You could throw the electrons away. It doesn't change your mass very much. And protons and neutrons are about the same. So if we took all of your protons and neutrons and put them in a bucket and measured them, or this 100-pound person, it would weigh 100 pounds. So far, so good. Now, it turns out that protons and neutrons are made of quarks. Quarks are a particle that most people haven't heard of, but just trust me, they were hypothesized in 64. They were pretty much proven in the 70s, and we accept these to be true. So inside protons and neutrons are quarks. And so now it would stand to reason that if you took all of the quarks and put them in a bucket, took them out of the protons and just threw them in a bucket, that would also weigh 100 pounds. But that's not true. If you do that, you find out that the quarks weigh about 2 pounds. So the protons and neutrons weigh 100 pounds. They're made of quarks, and the quarks weigh 2 pounds. So there's something not adding up here, right? Not making any sense whatsoever. And that's where it gets interesting and tricky and where Einstein comes in. Because inside a proton and neutron, it turns out you have three quarks, and these three quarks are zooming around. They're held together by a force holding them in, and they are traveling at near the speed of light. They're not traveling at the speed of light, but very, very fast. So they're zooming around. So they have a tremendous amount of energy because high motion, lots of energy. In addition, there has to be very, very strong forces holding them in because the protons are very, very small. And if you're traveling at near the speed of light and you're held in something the size of a proton, well, that means that there's very strong forces. And very strong forces give you a lot of potential energy. So what's important is that the quarks themselves being very light, they themselves have a lot of energy. And then we go full circle to where we started talking with Einstein's E equals mc squared. And so energy equals mass and mass equals energy. And so what's happening here is we are made of little particles that are very nearly massless. They have very little mass, but they're moving very, very fast. So basically, we are energy beings. Mass in the way that we think of mass doesn't exist. The only thing that exists is energy. And that, yes, can get you into some real, kind of crazy nuts and granola and crystal channeling kind of thing. It does not mean that all of this, this hokum is true. But it is true that we are made of energy, and matter doesn't, it's not what we think it is, which is totally
That's
groovy.
Yeah, that's the mind-blowing stuff when you think about it. Yeah, I like to
Mhm.
think I got my own theory that the quarks are where thoughts take place, and since people don't have a lot of thoughts or knowledge, it's lighter. Makes more sense. Less. You probably have very heavy quarks, Dr. Don. My quarks are so light. Okay, I think I have the lightest quarks on the planet,
Ah,
and makes more sense to me. Hey, so before I, discovered you, I used to have respect for something. I used to have respect for a little somebody called gravity, right?
mhm.
But I watched your videos and I found out that gravity is weak, man. If gravity's walking down an alley, I'm leaving with gravity. Whatever gravity has, I could take as long as I have a magnet. Okay. So, what is it about gravity that that ties all these special things? We hear so much special things about that are connected to dimensions, and there's slower clocks when you get near strong gravity, that time moves slower. And when you so can you explain some of the grand ideas behind gravity? Oh, besides the fact that we know it's very weak, all I need is a magnet, you're dead. But beyond that.
Well, we don't have 2 days, so I'm not going to be able to cover all the cool things about gravity. So we say gravity is weak, and it's true. On the other hand, gravity holds the solar system together. Gravity holds the galaxy together. So to say it's weak is incomplete. It's not the whole story because if gravity were the only weak thing, something else would be holding the solar system together or be holding the galaxies together. So there are places where it's stronger and places where it's weaker. When we talk about gravity being weak, however, um, it's because forces have sort of like a couple of things that go into them. For instance, with um, with gravity, you have the sort of inherent strength of gravity, but you have the mass of the objects that you're measuring. So if you have the sun and the planet, there's a strong force holding them together. If you have, I don't know, a person in a ping pong ball, it's a very small force holding them together. And it's not because gravity is any different. Gravity is the same for the person in the ping pong ball and the planet and the star, but the masses are very, very different. So that's the first thing you have to keep in mind when you talk about the force due to gravity, or for that matter, electromagnetism. it's not just the inherent strength of the force that matters. Furthermore, electromagnetism, which is much, much, much stronger than gravity intrinsically, but it's only true if you have two objects that have electric charge. But something like a star and a planet, they have very little electric charge. And so since they have very little electric charge, even though the intrinsic force is very strong, with zero charge, it doesn't matter how strong the force intrinsically is, there isn't a force there. And that's why it's not electromagnetism that governs how planets orbit, it's gravity, because gravity always it has mass and or not, it doesn't have mass, but gravity uses mass and mass is always there. Charge isn't always there. But all right, so that you got to keep that in mind. But now let's just kind of explain what people mean when they talk about the force as being weak. There are four known forces. There's electromagnetism, the strong and weak nuclear force, which are quantum forces, and gravity. And if you look at something the size of a proton, which is very small, it's not a place that we have any like day-to-day experience because it's really small. On that scale, the strong force is hugely strong. It's the strongest. Electromagnetism is about 1% the strength of that strong force. Weak force is about 0.001%, and gravity is basically zero. But if you go to a bigger distance, the size of an atom, the nuclear forces have zero effect because they're very short-range forces. It's like Velcro. Velcro could hold things together pretty strong, but you get a little bit away from the touching one another, and Velcro doesn't matter anymore. That's true of the nuclear forces. So on bigger scales, on like atoms or stars, the only ones that matter is electromagnetism and gravity. But if if you have things with no charge, then gravity wins. So it's very tricky when you start talking about the strength of the various forces. There's other stuff going on, but everything being equal, gravity is a very weak force. But it's just the other forces like don't apply in certain places, and therefore gravity wins, I guess.
So now, so now then, so then, how is this possible then? This special relativity, where I go the strong, you're closer to a strong gravity pull,
Mhm.
and now time goes slower. Is this a real thing? We hear
It's a
of
real thing.
this,
It's absolutely a
especially. How
real
is this
thing.
possible?
It's the same sort of thing. It's much more complicated, where I told you going partly through time and partly through space. That's when there isn't any gravity. But it turns out that if you're basically space and time near a heavy object is bent more. And it's that bending that causes time to be slower. Now, this sounds crazy, and it's not something that it's easy to measure, but this is absolutely astonishing. So there's a group of researchers in Colorado at the National Institute of Science and Technology. And what they did is they have these super duper crazy accurate clocks, ridiculously crazy clocks. Like in the history of the Earth, they might have lost a little bit less than a second if one of them was off a little bit. It's crazy. So they took two clocks that were identical, they synchronized them, and then they put them on a jack and they lifted one clock a foot, so 30 centimeters. And that clock ran faster because it was in slightly lower gravity than the clock at sea level. They brought it back down. The clocks were synchronized. They put the other one up. This one ran a little bit faster. And it had to do with the difference in time from a single foot separation. And, so it's true. We measured it. It's real. It's completely bizarre, but it's a real thing.
And do you guys do tests on this? Like you've done the test at Fermilab, you've done tests on something similar because they say it's inconsequential until you get to light speed, right? Or close to it
Well,
because it's
which
very
the we're talking separate things, the speed of light or the gravity.
this
They
this
kind of
this
relate.
the decay the time slowing. So like
Is time
I
slowing due to speed? Because
do
that's
this.
something we do here. We don't do gravity here. Time is
Okay.
slowing due to speed. We do here. And yes,
I guess I'm crossing the two because so time slows because of speed as well. So I know
right.
you
These
guys
are
did some
right. I'm
these
just
are
saying that
completely
they're
separate.
separate things.
But
Um,
so then there's two things that actually can slow down time. It's speed
yes,
and then gravity also. So I know you've
yes,
done work with like pions decaying slower,
hmm
right?
absolutely.
So is it the same logic in effect that, why does that happen?
Well, that has to do with the fact that everything now, forget gravity. That's way more
Okay.
complicated. Let's here on the surface of the Earth, yes, there's gravity, but it's not strong enough that general relativity really makes much difference. Um, but the speed thing, remember, all objects travel through space-time at the speed of light. And so if something travels very, very quickly through space, its ability to travel through time is slower. And that's, I mean, the easiest way to think of this is just think of like a compass, like for a Boy Scout, someone out camping. So you have a compass, it's got a circle and an arrow, and you can turn the compass around, right? But the size of the arrow doesn't change. So you turn the compass, and it might be starting out pointing north, but then you turn it, and now it's not pointing north anymore. It's pointing east or something. And so if you think about like north and east as space and time, or maybe a clock's a better way of thinking about it. The uh, the the hand points up to 12 o'clock, or it can point horizontally to 3 o'clock. But the length of the hand doesn't change. And so if, say, up is space and horizontally is time, then if you're going upward, then you're traveling through space very rapidly. You're traveling at the speed of light, so you're like light. And if you are not traveling through space very quickly, you're traveling through time very quickly. So us sitting here stationary, we're moving through time at the speed of light. But here at the lab, we can accelerate things to traveling basically at the speed of light. And if we do so, we find that, in fact, their clocks really do slow down. And there's no question our whole apparatus wouldn't work if we didn't take this into account.
Wow. See, this is why I like the information that you have to give, because you're talking about the science fiction that's real. You're talking
It's true.
about the real stuff, the
Yeah,
trippy stuff over here that mind-blowing things. Things are slowing down at speed. You make me think I just need to go as fast as speed of light. I'll never age. That's that's as simple as that.
it is true. It is true. But people around, if people who weren't going at the speed of light, you wouldn't age, they would. So, you'd go out and come back, they'd be gone.
So, and who knows what would be here?
Yeah,
So,
something else.
well, let me ask you this, and I'll ask you one more question here because I think this is kind of one of the most mind-blowing things that I've heard you discuss. So, tell me about 5 billion years from now. What do we know about the end? We know how the universe started. How do we know how the universe is going to end? What's gonna happen here?
Well, the stars will run out of fuel. Like there's most stars, it's like a fire. You start the fire and then you just let them go, and eventually they run out of fuel and they die away and they fade. So 5 billion years is not very long. I mean, our sun will it'll be very dim by then, but it'll still be around. In about 1 billion years, the sun will expand and it'll get hot and it'll melt, destroy the Earth. So we won't be here, but the sun will still be here. So that's the first thing. It's basically over bigger time scales, more than 5 billion years, 10, 20, 50. The stars will just start dying out. However, simultaneously, the universe is expanding, and the expansion is going faster and faster. And so this is kind of a bizarre thing that galaxies, which are a certain distance apart, because of the expansion of space, they are moving away from one another and they're moving away faster and faster. So in the very distant future, there will come a time where some future humanity will look out in space and they will only see one galaxy, the galaxy in which we exist, and everything else will be blank. And of course, those stars will be dying. So, everything it'll be like embers dying away. But part of the reason that we can't see it is because the light is fading away. But partly it's because they've moved so far away you can't see them anymore.
Oh my God.
Yeah, it's
But we'll
called the
still
heat
have.
death of the universe.
Tell me, at least we'll still have Netflix then. Will we at least be able?
No, because by then they'll like put it in your brain and you won't even need Netflix. It'll just, you know, it'll be something better.
Oh, you're right. You're right. So there is something to look forward to there. Hey, well, you know what? Hey, I really loved speaking with you. You share so much information that I mean, it probably seems very simple to you, and you probably repeat it so many times now. But for us and the people listening, it's fresh and it gets our imaginations going. So, where should we send people, or is there anything else that you're working on soon that you want to let the people know about? I know you have so many great books. I loved your you got a little great educational series that you put out about a year ago that I really liked too.
Well, if people are interested in books, videos, scientific articles, magazine articles for the public, probably the easiest place is to go to drdonlincoln.com. So DRDON Lincoln.com. And there's links to various things. If people are interested, if they want to go to the Fermilab YouTube channel, we have a couple hundred videos, 10 minutes long, about all of these topics, which are informative and occasionally fun. And then, as you say, I have books. You can see those on Amazon. And basically, they're about the type of topics that we talked about here. And if someone's interested, take a look.
One more question: are you going to grow the mustache back?
I don't know.
It was the best mustache in science. Come on, you had Neil deGrasse Tyson beat by a mile.
well, yeah, I mean, in every way. Oh, sorry, I digress. Um, yeah, I don't know. I had the mustache for a long time. Um, People seem to run 50-50 on it, so I haven't decided. It might come back.
All right. Well, you look young these days. So, thank you for joining today. I really appreciated this, and people are gonna love the information too. So
Thanks for
enjoy
inviting
the
me.